Good morning everyone. I am L, Honorary Chairman of the Lit Research Institute. Let's take a look at Shogi paper of AlphaZero. Well, we Lit present. The 15 topic we offer is, why is computer Shogi so strong? Closing square bracket. First, let's look at AlphaZero's treatise. Title: Mastering Chess and Shogi by Self-Play with the General Reinforcement Learning Algorithm. Abstract. The strongest programs are based on a combination of sophisticated search techniques, domain-specific adaptations, and handcrafted evaluation functions that have been. The game of chess is the most widely studied domain in the history of artificial intelligence, refined by human experts over several decades. In contrast, the AlphaGo Zero program recently achieved superhuman performance in the game of Go by tabula rasa reinforcement learning from games of self-play. In this paper, we generalize this approach into a single AlphaZero algorithm that can achieve tabula rasa, superhuman performance in many challenging domains, starting from random play, and given no domain knowledge except the game rules. AlphaZero achieved within 24 hours a superhuman level of play in the games of chess and shogi, Japanese chess, as well as Go, and convincingly defeated a world champion program in each case. The study of computer chess is as old as computer science itself. Babbage, Turing, Shannon, and von Neumann devised hardware, algorithms and theory to analyze and play the game of chess. Chess subsequently became the grand challenge task for a generation of artificial intelligence researchers, culminating in high-performance computer chess programs that perform at superhuman level 9-13. However, these systems are highly tuned to their domain, and cannot be generalized to other problems without significant human effort. A long-standing ambition of artificial intelligence has been to create programs that can instead learn for themselves from first principles. 26. Recently, the AlphaGo Zero algorithm achieved superhuman performance in the game of Go by representing Go knowledge using deep convolutional neural networks. 28, trained solely by reinforcement learning from games of self-play. 29. In this paper, we apply a similar but fully generic algorithm, mastering chess and shogi by self-play with the General Reinforcement Learning Algorithm. Abstract. The game of chess is the most widely studied domain in the history of artificial intelligence. The strongest programs are based on a combination of sophisticated search techniques, domain-specific adaptations, and handcrafted evaluation functions that have been refined by human experts over several decades. In contrast, the AlphaGo Zero program recently achieved superhuman performance in the game of Go by tabula rasa reinforcement learning from games of self-play. In this paper, we generalize this approach into a single AlphaZero algorithm that can achieve tabula rasa, superhuman performance in many challenging domains, starting from random play, and given no domain knowledge except the game rules. AlphaZero achieved within 24 hours a superhuman level of play in the games of chess and shogi, Japanese chess, as well as Go, and convincingly defeated a world champion program in each case. The study of computer chess is as old as computer science itself. Babbage, Turing, Shannon, and von Neumann devised hardware, algorithms and theory to analyze and play the game of chess. Chess subsequently became the grand challenge task for a generation of artificial intelligence researchers, culminating in high-performance computer chess programs that perform at superhuman level 9-13. However, these systems are highly tuned to their domain, and cannot be generalized to other problems without significant human effort. A long-standing ambition of artificial intelligence has been to create programs that can instead learn for themselves from first principles. 26. Recently, the AlphaGo Zero algorithm achieved superhuman performance in the game of Go by representing Go knowledge using deep convolutional neural networks. 28 trained solely by reinforcement learning from games of self-play. 29. In this paper, we apply a similar but fully generic algorithm, which we 1. Archive 1712.01815 v1 CSAI, 5 December 2017. Call AlphaZero to the games of chess and shogi as well as Go, without any additional domain knowledge except the rules of the game, demonstrating that a general-purpose reinforcement learning algorithm can achieve tabula rasa, superhuman performance across many challenging domains. A landmark for artificial intelligence was achieved in 1997 when Deep Blue defeated the human world champion. 9. Computer chess programs continued to progress steadily beyond human level in the following 2 decades. These programs evaluate positions using features handcrafted by human grandmasters and carefully tuned weights combined with a high-performance alpha-beta search that expands a vast search tree using a large number of clever heuristics and domain-specific adaptations. In the methods we describe these augmentations, focusing on their 2016 Top Chess Engine Championship (TCE) Seek World Champion Stockfish 25. Other strong chess programs, including Deep Blue, use very similar architectures. 9. 21. Shogi is a significantly harder game, in terms of computational complexity, than chess. 2. 14. It is played on a larger board, and any captured opponent piece changes sides and may subsequently be dropped anywhere on the board. The strongest shogi programs, such as Computer Shogi Association (CSA) World Champion Elmo, have only recently defeated human champions. 5. These programs use a similar algorithm to computer chess programs, again based on the highly optimized alpha-beta search engine with many domain-specific adaptations. Go is well suited to the neural network architecture used in AlphaGo because the rules of the game are translationally invariant, matching the weight-sharing structure of convolutional networks, are defined in terms of liberties corresponding to the adjacencies between points on the board, matching the local structure of convolutional networks, and are rotationally and reflectionally symmetric, allowing for data augmentation and ensembling. Furthermore, the action space is simple. A stone may be placed at each possible location, and the game outcomes are restricted to binary wins or losses, both of which may help neural network training. Chess and shogi are, arguably, less innately suited to AlphaGo's neural network architectures. The rules are position-dependent, e.g. pawns may move 2 steps forward from their second rank and promote on the 8th rank, and asymmetric, e.g. pawns only move forward. And castling is different on king side and queen side. The rules include long-range interactions, e.g. the queen may traverse the board in one move, or checkmate the king from the far side of the board. The action space for chess includes all legal destinations for all of the players' pieces on the board. Shogi also allows captured pieces to be placed back on the board. Both chess and shogi may result in draws in addition to wins and losses. Indeed, it is believed that their optimal solution to chess is a draw. 17, 20, 30. The AlphaZero algorithm is a more generic version of the AlphaGo Zero algorithm that was first introduced in the context of Go. 29. It replaces the handcrafted knowledge and domain-specific augmentations used in traditional game-playing programs with deep neural networks and a tabula rasa reinforcement learning algorithm. Instead of a handcrafted evaluation function and move ordering heuristics, AlphaZero utilizes a deep neural network P, V, equals F theta, S, with parameters theta. This neural network takes the board position S as an input and outputs a vector of move probabilities P with components par equals PR, A, S. 2. For each action A, and a scalar value V estimating the expected outcome Z from position S. V approximately equals E, Z, S. AlphaZero learns these move probabilities and value estimates entirely from self-play. These are then used to guide its search. Instead of an alpha-beta search with domain-specific enhancements, AlphaZero uses a general-purpose Monte Carlo tree search (MCTS) algorithm. Each search consists of a series of simulated games of self-play that traverse the tree from root to leaf. Each simulation proceeds by selecting in each state SA mover with low visit count, high move probability and high value, averaged over the leaf states of simulations that selected A from S, according to the current neural network f theta. The search returns a vector pi representing a probability distribution over moves, either proportionally or greedily with respect to the visit counts at the root state. The parameters theta of the deep neural network in AlphaZero are trained by self-play reinforcement learning, starting from randomly initialized parameters theta. Games are played by selecting moves for both players by MCTS at pi t. At the end of the game, the terminal position street is scored according to the rules of the game to compute a game outcome Z-1 for a loss, 0 for a draw, and +1 for a win. The neural network parameters theta are updated so as to minimize the error between the predicted outcome Vt and the game outcome Z, and to maximize the similarity of the policy vector Pt to the search probabilities pi t. Specifically, the parameters theta are adjusted by gradient descent on a loss function L that sums over mean squared error and cross entropy losses respectively. P, V equals F theta, S, L equals Z minus V. 2 minus pi log P plus C, theta, 2, 1, where C is a parameter controlling the level of L2 weight regularization. The updated parameters are used in subsequent games of self-play. The AlphaZero algorithm described in this paper differs from the original AlphaGo Zero algorithm in several respects. AlphaGo Zero estimates and optimizes the probability of winning, assuming binary win-loss outcomes. AlphaZero instead estimates and optimizes the expected outcome, taking account of draws or potentially other outcomes. The rules of Go are invariant to rotation and reflection. This fact was exploited in AlphaGo and AlphaGo Zero in two ways. First, training data was augmented by generating 8 symmetries for each position. Second, during MCTS, board positions were transformed using a randomly selected rotation or reflection before being evaluated by the neural network, so that the Monte Carlo evaluation is averaged over different biases. The rules of chess and shogi are asymmetric, and in general symmetries cannot be assumed. AlphaZero does not augment the training data, and does not transform the board position during MCTS. In AlphaGo Zero, self-play games were generated by the best player from all previous iterations. After each iteration of training, the performance of the new player was measured against the best player. If it won by a margin of 55%, then it replaced the best player, and self-play games were subsequently generated by this new player. In contrast, AlphaZero simply maintains a single neural network that is updated continually, rather than waiting for an iteration to complete. URL: https://archive.org/pdf/1712.01815.pdf. Bonanza method. Closing square bracket. The technology called machine learning has made it possible for artificial intelligence to imitate humans, and graduated from a programmer. As a result, we have made great strides in the development of artificial intelligence, but at the same time scientists and programmers are in trouble. It is a trade-off between interpretability and performance, that is, the higher the performance of artificial intelligence, the more it becomes impossible to explain why the performance has improved. This tendency has already become a premise or a kind of principle in the development of artificial intelligence. I don't know the reason, but I get stronger. Why is that happening at the forefront of modern science called artificial intelligence? Let's explain that from now on. Suddenly, do you all know the word black magic? In the world of fairy tales and fantasy, it's the magic used by witches to make mysterious medicines. If you stand in front of a simmering cauldron and throw in materials with a spell that doesn't make sense, you can make the desired medicine with smoke. I think many people have seen such a scene in an anime work. You may be surprised, but this black magic has become established as a slang in the world of machine learning, and it is a general term for technologies that do not know how they were born or why they are effective. Naturally, information science, which is a discipline that studies artificial intelligence, was originally a world dominated by logic and mathematics. It was a world where the reasons and theories could explain everything. However, in modern information science, especially in the field of artificial intelligence, black magic is becoming more and more influential. The influence of black magic naturally extends to Bonanza. Bonanza is a program that I developed, so I made it with careful attention to detail. Moreover, I understand the narrow area of the shogi program at the top level in the world. Even so, Bonanza has a lot of black magic built in, and the reason and reasoning are already largely unknown. If you don't understand the reason for the program, for example, you don't really understand why the numbers embedded in the program are good, or why the combination is effective. At best, it has been found to be empirically or experimentally effective. Let's explain a little more concretely. The current Bonanza improvement method is to automatically play about 3,000 games between the Bonanza to which it is applied and the previous version of Bonanza, if you think of any new improvements. At this time, the policy is that new improvements will be adopted when the winning percentage of the new Bonanza is 52% or more. I do not look at the content of 3,000 games of shogi individually, but measure them by statistical processing. To be precise, even if you try to examine the contents of shogi, you cannot examine it because you do not know the cause of victory or defeat of the game. This is because Bonanza's strength is already far above my level. Moreover, the improved work and the strengthening to Bonanza are far from the sense of being a shogi player, and the divergence cannot be reduced by reasoning. I have no idea where and how the successful improvements worked. In addition, the success rate of such improvements is less than 2% according to the rule of thumb so far. Even if you make some improvements and play 3,000 games, you can't confirm that it will be stronger twice in 100 times. For that reason, the current improvement work of Bonanza is almost the same as working by intuition in total darkness. It is a daily occurrence that the improvement that I thought will definitely work is not successful, and the fact is that I happen to be collecting the improvements that worked. So the improvements that happen to work seem more and more like black magic to me. One of the black arts, lazy parallelization. Let me introduce one concrete example of improvement equals black magic that worked for some reason. It's called lazy parallelization. This is not something I discovered, but it is a well-known event in the area of AI development for shogi and chess, and it is an important black magic that Bonanza has become much stronger by incorporating it. For that purpose, I would like to first explain the recent CPU situation. I will be a little more specialized, but please forgive me. I think everyone has heard the word CPU. CPU is an abbreviation for Central Processing Unit, and means Central Processing Unit. As the name suggests, it is the brain that processes and calculates the entire PC, so its quality is directly linked to the performance of the PC. Until a while ago, CPUs were evolving at a tremendous speed. After 18 months, the number of transistors, mesh-like integrated circuits, in the CPU doubled, and the flow of research and development continued to improve performance. The software was in a state where it could run at high speed without permission, even with the same code, just by following the flow. By the way, in Shogi AI, the processing speed of the computer is crucial. If the double speed is different, even the same software can win with a winning percentage of 70 to 80%, so even the developers of computer shogi are strong even if they have a free lunch. Free meal equals easy until a while ago. It was a situation where I could get used to it. However, giants of CPU vendors such as Intel gave up to some extent about CPU development on the extension line until then, about 10 years ago. This is because the technical limits are approaching the miniaturization of integrated circuits that support improved performance. The technology that was created there was multi-core. This is like putting 2 or more brains cores on one CPU. After that, CPUs with only one core, which is the same as before, are called single cores, 2 CPUs are called dual cores, and 4 CPUs are called quad cores. What is amazing about multi-core is that what was previously processed by one brain can be processed by 2 or more brains. This is called parallel processing. It can be intuitively imagined that parallel processing will bring about a significant improvement in performance. In fact, some programs and software have benefited from it. However, it is for shogi programs. Until recently, the efficiency improvement of parallel processing was not as effective as expected. I won't explain the details of the reason here, but in the task of searching for a shogi hand, the usual parallelization in the form of multiple cores working together to do one process does not work very well. It was. If you compare it to the kitchen of a restaurant, normal parallelization is when multiple chefs work together to make one dish. This certainly seems to be able to cook fast. However, that also depends on the number of chefs. There is no problem if 2 chefs work together to prepare a serving of food. In fact, even a shogi program can search very efficiently when processing in parallel with 2 cores. But what if the number of chefs is 8, 16, or 64? At this point, it seems that efficiency will become worse and worse. In the first place, the kitchen is full of people. Actually, even in a shogi program, parallel processing with a certain number of cores or more makes it extremely difficult to improve performance. If you're not good at it, the performance may deteriorate due to parallel processing. However, a new search method has been born in the last 3 years. To be precise, it may be correct that the old method has been reviewed. That is lazy parallelization. This method is a very simple program, and in a very simple way, it is parallelization in the form of multiple cores perform one process separately. Lazy parallelization is when multiple chefs compete separately to create a single dish. And we will provide our customers with the fastest cooked food. Of course, it is not made completely independently. Each core works separately, but the good information that each core happens to discover is shared throughout. I think this loose cooperative relationship is described as laziness. Why does this method of sharing good information appropriately work? Various explanations are being attempted. However, it is not easy for experts to explain the reason perfectly. If I dare to explain it, would it be something like, I tried it and it worked? It's not explained at all, but in a sense there's no better truth. That's all about Bonanza and black magic, but I'd like to make it clear that I'm not afraid of black magic or that Bonanza will turn into black magic. Because Bonanza is designed to fight against professional shogi players who are much stronger than me. Today's artificial intelligence is required to deviate from the intuition and expected performance of programmers. That's why Bonanza has to be beyond my understanding. Shogi may result in draws in addition to wins and losses. Indeed, it is believed that their optimal solution to chess is a draw, 17, 20, 30. The AlphaZero algorithm is a more generic version of the AlphaGo Zero algorithm that was. It replaces the handcrafted knowledge and domain-specific augmentations used in traditional game-playing programs with deep neural networks first introduced in the context of Go. 29. And a tabula rasa reinforcement learning algorithm. Instead of a handcrafted evaluation function and move ordering heuristics, AlphaZero utilizes a deep neural network P, V, equals F theta, S, with parameters theta. This neural network takes the board position S as an input and outputs a vector of move probabilities P with components par equals PR, A, S. 2. For each action A, and a scalar value V estimating the expected outcome Z from position S. V approximately equals E, Z, S. AlphaZero learns these move probabilities and value estimates entirely from self-play. These are then used to guide its search. Instead of an alpha-beta search with domain-specific enhancements, AlphaZero uses a general-purpose Monte Carlo tree search (MCTS) algorithm. Each search consists of a series of simulated games of self-play that traverse a tree from root to leaf. Each simulation proceeds by selecting in each state SA mover with low visit count, high move probability and high value, averaged over the leaf states of simulations that selected a from S, according to the current neural network F theta. The search returns a vector pi representing a probability distribution over moves, either proportionally or greedily with respect to the visit counts at the root state. The parameters theta of the deep neural network in AlphaZero are trained by self-play reinforcement learning, starting from randomly initialized parameters theta. Games are played by selecting moves for both players by MCTS at ~pi t. At the end of the game, the terminal position street is scored according to the rules of the game to compute a game outcome Z, -1 for a loss, 0 for a draw, and +1 for a win. The neural network parameters theta are updated so as to minimize the error between the predicted outcome Vt and the game outcome Z, and to maximize the similarity of the policy vector Pt to the search probabilities pi t. Specifically, the parameters theta are adjusted by gradient descent on a loss function L that sums over mean squared error and cross-entropy losses respectively. Ref. https://diamond.jp/articles//127697. Can computer brains beat humans? The theme of memory and brain science is computer shogi. In the second Deno match held in 2013, the computer won the Active Pro for the first time with 3 wins, 1 loss and 1 draw. Shogi is a complicated game with a wide board and the reuse of pieces. For a long time, it was difficult for computers to have knowledge comparable to humans. So why did he become stronger than a professional shogi player? Kei Sato, Panasonic researcher, gave a lecture at the 17th Natural Sciences Research Organization Symposium, Brain Science of Memory How We Forget to Remember, held on September 23. From the history of shogi, there was a very interesting story about how computer shogi became stronger, why and in the future. The history of computer shogi dates back to the 1970s. It developed rapidly from the mid-2000s. The reason is the important technology that supports the strength of the current program has developed rapidly, explains Mr. Sato. Specifically, this includes machine learning of evaluation functions and full-width search, see figure. By making full use of these technologies, computer shogi has reached the strength to reach the professional level at once from the amateur level. You might think that the improved computing power of computers has made it better than humans, but that's not all. In 1997, the computer surpassed the human champion of chess, but the complexity of chess is 10 to the 120th power, while the complexity of shogi is 10 to the 220th power, which is quite complicated. It is impossible to beat humans just by increasing the speed of computers, and Mr. Sato emphasizes that the progress in software is very large. Search and evaluation function correspond to reading and perspective. So how does the computer specifically decide the move of shogi? Normally, when a human plays shogi, the move is decided by reading and big picture judgment of the situation. In the case of a computer, the reading is the search and the big picture is the evaluation function. In computer shogi, we basically search for all hands, including those that humans do not think. The search is deep and step by step, but the search is stopped at a certain depth because the search cannot be done until the end due to the time limit. The superiority or inferiority of the situation when it is cut off is scored by the evaluation function. The evaluation function is a function for quantifying the superiority or inferiority of a situation so that the computer can judge it, and the computer selects and points to the procedure with the highest evaluation, that is, the highest numerical value. The characteristic and problem of computer shogi is that it searches for all hands, so there is little reading through, but there is a lot of waste. Therefore, even though we read millions of situations per second, we sometimes lose to humans, Mr. Sato. In addition, the evaluation function quantifies all aspects, but the quantification was created by humans. Humans usually find it very difficult to create an accurate merit function, even if they don't score and think about it. Machine learning, that became the driving force to defeat professional shogi players. The challenges in creating a strong computer shogi are: do not search for useless hands, but search deeply for good-looking hands, and create an evaluation function that accurately quantifies the superiority or inferiority of the situation. It is aggregated into one. Regarding the latter, a program called Bonanza, that appeared in 2006, greatly contributed to the numerical work of the evaluation function. It succeeded in automatically adjusting the parameters by machine learning, in the quantification work that was conventionally performed by humans. It is said that this success led to a dramatic improvement in the performance of the shogi program. And in recent years, machine learning using professional game records has been very successful. However, it does not mean that you can remember the game record as it is. Simply memorizing it can only be used in situations where it is exactly the same. The aim is to acquire the meaning of the move. Specifically, we will learn from professional moves what kind of situation is good and what kind of move should be explored deeply. For example, what is currently being done is learning by comparing moves. In a certain situation, there is a move selected by a professional correct answer, and a move not pointed incorrect answer. Adjust the evaluation function so that the correct answer has a higher score than the incorrect answer. In addition, when a professional chooses a move, the computer can only see one move, while the reading is up to a few moves. In order to deal with this problem, we will introduce search reading in the learning course, advance to a few steps, and then compare it with the correct answer. In this way, the evaluation actually thought by the professional is associated with the evaluation actually thought by the computer. Future: do you learn shogi from a computer? According to Mr. Sato, it is almost certain that computer shogi will beat the top human players in the near future. However, it seems that winning over humans equals not acquiring knowledge that exceeds human thinking. The current computer shogi surpasses humans in the number of mistakes and the depth of reading, but in the first place, machine learning imitates human hands, and it is hard to say that it has reached the big picture of humans. Further improvement: there is a lot of room for it. There are various improvements, but for example, what kind of game record should be learned to make a strong program, and what kind of tactics should be emphasized to make a strong program. Regarding tactics, it seems that tactics such as Anaguma, Silver Crown, Yakura, etc., that make a solid enclosure are ranked high. comparing the differences in tactics between a program that was actually learned using importance and a program that was simply learned without using it, selecting a tactic that is easier for the computer to learn by learning using importance. As a result, it turned out to be quite strong. In this way, now that the goal of computer shogi to beat humans is being achieved, computer shogi is at a major turning point. Mr. Sato explains that there are two directions, a direction to pursue further strength and a direction to emphasize the relationship with humans. Is it possible to learn a strong program regardless of the human game record in the direction of seeking strength? And in the direction of seeking relationships with humans, it is possible to teach human shogi or create problems such as sume shogi. It is said that computer shogi has become stronger by imitating human beings, but it seems that the era of becoming stronger by having computers teach shogi is just around the corner. Ref. https://news.minavi.jp/article/nins_kyoku-2/. Thank you.